And so today the plan is to talk about theory of sets, the most boring topic because it's all about theory and not practice. But this theory is used in all of the publications which have any kind of math formulas. So you need to know the terminology, you need to know how different symbols work. So this is all about symbolics and notation. So it's difficult if you've never seen theory of sets before, it's difficult to get it on the first try, but we will repeat it multiple times, so you'll get used to that, and then it will be fine. Okay, so even if you don't get it on the first try, just go through the lecture again, publish that online already. You will see all the symbols over and over again, so you'll get used to them, you'll be fine. All right, so theory of sets was developed in not that far ago, 100 years ago, a little bit more, by George Cantor. And this was a little bit crazy theory about infinity. So people try to understand what infinity means, and if it's something that you can work with, or it's just something imaginary that you cannot work with. So his proposal was that you actually you can understand infinity in better ways than it was before him. And we will learn only finite things typically, and very standard sets. We will not go into paradoxes of that theory because you have a lot of interesting things going on there. Gilbert Hotel and other interesting paradoxes of that theory, but we will not get into any of it. You can look it up if you're interested in that. We'll just define set as some sort of set of different objects, and it could be any kind of object. It could be numbers, it could be chairs, it could be rooms, it could be anything you want. And it could be finite set, where you can have a particular number of things, or it could be infinite set, where you have an infinite number of numbers, like real numbers, for example. You have infinite number of real numbers, right? So the thing is that we can write that set as some uppercase letter, A, B, C, and so on, equals, and then you listing all of the elements, which are called elements of that set. And this could be numbers, it could be colors, it could be whatever you want. Okay, it's very abstract right now, but set could be practically anything you can imagine, and you can list different things. Now it's very important to remember that sets, you don't need to double the same thing multiple times because it's not changing the set. So if you have included number 2 twice in the set, it's still single number 2. Okay, so set of 2 is the same as set of 2. Also, order of elements doesn't matter really. You don't care about particular order of elements in that set. So everything you put in this curly brackets, it's elements of the set, and you can include anything you want. So you're writing A equals curly brackets, whatever elements you want. This is set. Now, subset of set is also set. Subset is just part of the bigger set. So let's say integer numbers are subset of real numbers. So it's just part of that set. And it's also set, obviously. Now, yes.
In previous lecture science, why the sets A have 5 elements?
I'm sorry?
Why the sets A have 5 elements?
Because we're missing comma here. This is why. Thank you.
Okay.
All right, so it's just 5 elements set, 5 numbers. Five. Okay, this symbol means belongs to, that kind of inclusive thing, or member of, which means if some element, that symbol, and you're showing set, this is member of that set or subset. For example, 5 belongs to all the x's which are between 0 and 10. So this is true. So 5 is between 0 and 10. So that's how you write it. Sometimes people also using kind of bar. straight bar from top to bottom. I don't know even how to call that symbol. Do you know the name of that symbol where you have just line from top to bottom? It's also used instead of column sometimes. So if you have the computer and replace this thing, that thing. So sometimes in some articles you see that symbol, and sometimes you have that symbol. Same thing. In that case, okay. So 5 belongs to that set. 5 doesn't belong to that set. All x's which are larger than 10. Please sign in. This is false statement. All statements about sets might be true or false. So this connects us somehow to mathematical logic, which we'll mention a little bit. X does not belong to A means that this is not a set. Okay, any questions so far? So this is relations between elements and sets as we define them. And 5 doesn't belong to that set. So this symbol is subset. So A is subset of B, and it means that all elements in subset A belong also to B. So B kind of including A. All right, but they could be also equal, which means they have exactly the same elements, all of them. And this is why that kind of almost equal sign. This, if you're thinking about numbers, it will be like less or equal, right? So in sets, it's belongs or equal type of thing. So all of the elements of A are in B. And this means that all of the elements of B in A. So if both of them are true, then both sets are equal. Which means if all elements of A are in B and all elements of B are in A, they should be equal. They are the same set. Okay? And this is just examples that red and green belong to a set of all colors as subset. And 1, 2, 3 belongs to 1, 2, 3, 4, 5, and so on. And again, order of numbers doesn't matter. I could tell you like 5, 4, 1, 2, 3, or whatever. Any order is fine. Doesn't matter. Questions so far? So those are the symbols. Now, as I said, equal sets is when one belongs to another one and another one belongs to the first one. If it goes both ways, each one of the sets is subset of the other one, then both of them are equal. And I mentioned also that this bar means such that. So if you have X, then column is X such that and some property of X. Okay, as we seen on the previous one here, that kind of thing. That's how you describe particular elements of the set if you don't want to list them all, or you cannot list them all. So these sets are equal if and only if they have exactly the same elements. So these sets are equal, and doesn't matter the order of elements. This is also same description of that set. It's like 1, 2, 3 set. So X equals to 1, 2, or 3. But these sets are not equal because you have here 4 elements and here you have 3 elements, right? Now, union and intersection of sets. So union of sets means you're taking 2 sets and you're taking all of the elements that you have in both of them without repetition. You don't need repetition between the numbers because numbers or elements, because they are the same value, okay? So for example, and the symbol for union is that type of symbol, okay? Almost U letter type of thing. Sometimes we are using also plus. Some textbooks even using plus to add 2 sets if it is clear from the context what plus means. So plus between sets means union of 2 sets, having elements from both of them. So let's say union of 1, 2, 3 and 3, 4, 5 will be 1, 2, 3, 4, 5. Okay, pay attention that both of them have 3, but you counting that only once. Because in sets you don't need to double that information. You have 5 element vector, which is union. Intersection is only common elements. It's subset of common elements for 2 sets. If both sets have exactly the same elements, this is their intersection. And intersection, you're writing it with that symbol, which is inverted U type of symbol, or multiplication. in mathematical logic. Yes, question?
It's the same as probability. Like in probability, when we
Yes.
say the probabilities intersect, it's the and.
Yes. And this is why in probability you're using the symbols as well when you're connecting two sets and you have Venn diagrams which are intersecting. This is coming from theory of sets. Yes, this is a notation of theory of sets. People just don't learn it as theory of sets. They just like, oh, use that symbol and whatever. Okay. And these are the functions in MATLAB, and I will give you functions in MATLAB as well for all these functions that you need to use. So union is that union of the two sets, A and B, and you can write it as vectors or any cell structures or whatever in MATLAB. And intersect is intersection of two sets in MATLAB between A and B. So intersection of 1, 2, 3 and 3, 4, 5 is that element 3, which is common to both of them. You might have multiple common elements, so you'll have bigger subsets. Any questions so far? All right. Complement is like almost negate of something, it's like not something. So complement is, in a sense, subtraction of sets, which is practically everything which is not included in one set, but in the second one, it doesn't include. Okay, so this is the idea. Typically, we write that as A naught, like in mathematical logic and Boolean logic, if you know that from electrical engineering. But this is a symbol for negation of something, like not A, not in A. So for example, A are all real numbers x such that x larger than 5. So all numbers, real numbers higher than 5. So not A, which is complement of A, will be all the numbers which are not larger than 5. Means smaller or equal to 5. All right, so this is the other part. So relative complement of A with respect to set B is like difference between the sets. And in MATLAB, you would just write command set diff. It's difference of sets. Again, it's everything which is in that set. Okay, and you're subtracting that set. So you're practically removing those two elements from that set. Almost like a minus sign. You're removing, pulling out these elements. And it's like backslash, which you use as symbol of that minus sign, right? So for example, all real numbers minus rational numbers will be irrational numbers, right? If you negate A itself twice, you get A back, right? Because it's like everything which is not A and everything which is not A, which is A itself. Any questions so far? Compliments? And Venn diagrams, which you've probably seen before in probability theory or some other places, just graphical representation of different sets, their intersections, their properties of some kind, and how you compute different things geometrically, just visualization part. So Venn diagram says like we can represent particular set as some sort of blob, circle, or whatever it is, some other shape. And we color code them with particular color. Let's say green is a C set, red is A set, B is blue set, and so on. Okay, and you can draw that they have some common elements, they don't have some, and some other elements are not common. So common elements are their intersection of these ellipsoids, okay? And not common elements are the elements where you have the pure color and they do not overlap with other things. And also you need to know that this entire thing is typically, as in probability, called omega, which is entire space of all of the possibilities, which is universal group, universal set. And this universal set includes entire universe, everything, okay? So if you're doing, for example, not C, not B, and not A, it would be like everything else, it would be all the white space around, okay? Which is omega minus A, B, and C, right? So you can do all kinds of manipulations to get particular parts and intersections of the sets. So let's say this part here, in my cursor, right? Okay, so this part is intersection of A, B, and C together. This part is intersection of A and C when you get in that part. So let's say A unified with B, so it will be A and B together, so it will be that part. So going on B and then also A, so it includes both of them. All right, so this will be union of A and B. Union of A and B and C will be everything which is not white practically. All right, so it's like all of them together. This will be the shape of that entire thing. A intersection with B will be that part here. This A intersection with B, where they cross, regardless of where C is. Now, A intersection with B, as we detected before, and union with C will be that piece plus C. Okay, that kind of thing. That will include the entire C plus that intersection, which is that segment which is sticking out to the bottom. And then this one is more interesting. A complement union with B. So it has to include B somehow. But what is A complement in that case?
Everything except A. So
It's everything except A. Okay. So it would be practically everything. Okay. Except A. All of the white space, all of the blue space, green space, except that part. Okay. So drawing here all of these lines, which are complement of A, and you need union with B. So it needs to include the entire B. So what would that be?
E and C, except for the part of C
No.
that's in A.
Practically, it will be everything except that moon shape,
Yeah.
like space of A. Okay. So it will include B because it's union with B, so you need to include B. And everything else except A. But part of A is also overlapping with B, so you still need to include it because it's part of B as well. But you need not A, which is all of the space around it. So include practically everything except the space where you have only A and not B. Okay, so include everything except the moon. This will be that union of not A and B. Any questions? Okay, we will be working a lot with different standard sets. So we need some definitions for them. First of all, you have empty set with no elements. Nothing, practically, which was kind of interesting definition of what it would even mean, nothing. Is there a thing which is nothing? Philosophical question, difficult question, like how you answer what is nothing. Can it even exist, nothing? Right, it's a deep philosophical question, and many people struggled with that type of thing, but we will not get into philosophy of that. We will just define that intersection of two different sets that have no common element is that zero set or nothing set. You don't have any elements in common, for example. Okay, so for us, it will be kind of more practical definition of what is empty set. And we will define that as that, like, crossed zero or just empty parentheses, empty brackets, curly brackets. Okay, this is empty set. Set of natural numbers, I will include zero in that set. Many textbooks do not include zero in that set. For convenience, I will not like use n, zero, or whatever other symbols. Just all the natural numbers, 1, 2, 3, 4, 5, and 0. Now, integer numbers, which are plus minus 1, plus minus 2, plus minus 3, and so on, it's called Z. That. So I believe this is coming from German name for whole numbers. It starts with the letter Z. Rational numbers are Q, which are all fractions. And this set is defined as some number x divided by some number y, where x and y are numbers in Z, and Z are integer numbers. So you have two integer numbers, and denominator should not be zero. So all, like y cannot be zero. So it's like set of Z minus 0. Okay, so making that complement of 0, removing 0 from that subset, so y cannot be 0, but it could be any other whole number. Okay, and this is what fraction is. real numbers are all of the rational and irrational numbers together, and C will be complex numbers, as expected. Typically, we'll be working with R and C, but sometimes we will need integers and other things. So you need to memorize these two. We will use these ones a lot, R and C. And omega, as I said, is a universal set which includes everything possible within the meaning of the problem. And again, this omega, you can define what that omega is. It could be probability space, it could be some other space, it could be all kinds of things. Right? Questions so far? So these are the symbols. Additional things that we will be using is functions. So functions, as we define them in calculus, and typically, again, people don't see that type of definitions in calculus. Some courses do that, some courses do not show that. You have classical mapping. So you're thinking about function as mapping from one set to another set. So you have domain and range, and you're mapping domain into range space. So you get mapping between particular numbers or objects or elements from one subset to some other subset. And this mapping could be anything. It doesn't even have to be mathematical in a sense. Okay, it's just how it's like lookup table. Like what do you do with particular elements of that set to get elements in the second set? This is how mapping works in general. And this is how you write it. And typically in math, we call it function, right? It has domain where variables, you have x, y, z, and so on. And you're defining that value of f on each element of set A to get elements in set B. So this is practically how you map from A to B. This is a description. So why is that important for us? Because we will be using that notation in that kind of way. For example, you want to map all numbers with some function to only positive numbers. So you'll say from R to R positive, which means all positive real numbers. Or from particular square, this is not square, it's rectangle actually, okay? So rectangle would be on first variable, you will have from number -1 interval to +1 interval, and then second interval will be from 0 to 1. Okay, so first variable x, for example, will be from -1 to 1, second variable will be from 0 to 1, and the result will be from 0 to 2. Okay, that kind of function, which is mapping two numbers, x and y, into one output, which is that thing. So this gives you practically dimensions or ranges of values in which you can operate your functions. This gives you information about dimensionality of things. And this is very important for linear algebra, because in linear algebra, you have a lot of dimensions of matrices, vectors, all of that stuff, okay? And you have multiple variables as well. So this, for example, maps that thing, and this would be that example of that type of function, which maps these numbers for x and y into that interval. Sometimes you want to write it even in shorter way. So this means like r squared, for example, means r times r, which means you have two elements in that vector. And in the first element, you have three elements in that vector, three variables, and all of them are r. It's like r times r times r. So you get x, y, z. All three of them are real values, and it is mapping it to vector of two values. Okay, so this function maps three-dimensional space into two-dimensional space, because you have only two elements here, x plus y, first element, and xz minus y is second element. So this vector has only two components. Okay, and this vector has three components. So it's from three components to two components. Reduction of dimensionality kind of function. Okay, any questions on that? Again, I understand a lot of symbols, a lot of abstract things, new notation maybe that you're not very familiar with. Hopefully we'll get used to all of that. We will not get too deeper into that, and a few additional symbols to make tons of fun from symbols. And I promise it's almost the end of that part of the lecture. Yes.
Previous slide, I see the cross. You cross over with
On the previous slide?
previous, yeah.
Yes.
The second line of function -1 and
This
1
one?
cross, yeah. What does that mean?
So these are two variables. It's multiplication practically. This cross is multiplication, but multiplication in dimension sense. Because I don't want to put dots there because dot has in linear algebra very different understanding, like different meaning. Okay, this is dot product. So these two vectors are multiplied in a sense of dimension, which means one variable is from -1 to 1 and second variable is from 0 to 1. Okay, this is just multiplying. Same thing will be with R. You'll be writing like R cross R cross R. So R squared is like R cross R, which means these are different variables. They are not really multiple. You cannot multiply sets. There's no meaning to multiplying sets. It's just you have multiple variables and their dimensions are R and R. So this is R squared. And this is why the symbol is kind of multiplication because R times R is R squared. But unless you define what it means, it stays meaningless, right? So this is my definition of what that thing is. So this cross is kind of multiplication, but not really. The symbol that you have multiple dimensions, multiple variables. That's what it means.
It is used in the vector.
Yes, it's like a vector. You have vector of two elements. It's R squared. Okay, and each element is R. That vector. Any other questions? Okay, so a few more useful symbols. Inverted A is for all or any. So these symbols are used a lot in literature, engineering literature. Inverted E, mirror E is exists. There exists something, some elements exist in subset, for example. Okay. This, if you cross A or cross E, it's like does not exist or not for all. Okay. This symbol means therefore. This is identical to. Arrow means just implies or then. It's
Guys, it depends between this and then the mark.
No, in mapping you have same symbol, but it's different meaning.
Yes.
So this is when you're writing in sets, not in the definition of the function, but yes, this is a great question. So in mapping you have the same symbol meaning different thing. So it's not that R implies R. It's from R to R. But that symbol means that you are going from statement A to statement B. So statement B follows from statement A. Okay. Maybe sometimes they're using kind of double arrow to differentiate between these two. This could be like double arrow like this one. But this is if and only if, which is true in both directions. From statement A follows statement B, from statement B follows statement A. So it's like both directions are true. End of the proof. And these are typically used in mathematical logic. And you can replace that thing as not, which is a complement bar above the letter. Sometimes they write that way. This is similar to union, but it's logical union for Boolean logic and other things. They're using that type of symbol just for you to know. We will not use it, but that symbol is for intersection, in a sense, between two logical predicates. So mathematical logics, they are using that type of symbols instead of more rounded corner symbols, okay? Just for you to know if you ever see anything like that, they are practically the same thing. Any questions on that? And again, we will be doing some of that, some other things we will not even use. Don't have to memorize any of it right now, but when we'll go through it, it's better for you to have that dictionary of things. Okay, a few examples. A is a subset of B, if and only if, for all X belongs to A. If A belongs to A, follows that X belongs to B. This is what it means. Practically, I wrote with symbols what I said. Okay, so mathematicians love to shortcut sentences into symbolics. And this is what that type of thing means. Now, A is a subset of B but not equal to B, if and only if for all X belongs to A means that X belongs to B as well, and there exists some X which is in B and not in A. Makes sense, right? So you have something which is in B but not in A, but otherwise all the elements of A are in B. Okay, so it's like regular symbol of all that is subset. Now A equals to B if and only if A is subset of B and B is subset of A. And again, this is logic sign of intersection, so both of them should be true. Okay, this is logical symbol for that. Yeah, if you see anything like that in mathematical literature or engineering literature, you have a lot of that in signal processing, controls, and other places. Just you will know the symbols, what they mean, how to translate them into regular language. Okay, so this is the end of that particular lecture. Any questions?